Swayam Prabha. Digital India. Educated India.
Welcome back to a new lecture on control systems. So over the past few lectures we've discussed these two properties at some length, of course while staying within the limitations of an undergraduate course. So in the sense that if you go for a course on multivariable control, say at the graduate level, you would most likely be dealing with more sophisticated linear algebraic terminology like invariant subspaces and so on, and that will help you see these ideas of controllability and observability, and then those of controllable subspaces and so on and so forth, right. But those of course we shall not be dealing with within the precincts of this course. So for the purpose of this course we have established at least this much connection, that a minimal realization corresponds to one which is fully controllable and observable. And what is a minimal realization? It emanates from a transfer function which has no redundancy, that is whose numerator and denominator polynomials are irreducible, they have no common factors, right. So if you start from a transfer function with no poles and zeros in common, no matter how you realize it in the state space domain, you shall always end up with a fully controllable and observable realization, right. So that is essentially the crux of the matter. Of course you can artificially create if you so desire. So for example, if someone wants to write 1 upon s plus a as half upon s plus a plus half upon s plus a, and then realize it as two integrators, yeah, in a parallel sort of a realization, then of course we can't help it, yeah. But these are defective cases where you are deliberately introducing this sort of a redundancy to prove me wrong, in the sense that, well, look, I started with a transfer function that has no pole and zero in common, and yet I came up with a realization which is really not minimal, right. So apart from these sort of pathological cases, if we in general start with a minimal transfer function, that is an irreducible transfer function, we will invariably end up with a state space realization, yeah, which is also fully controllable and observable. One way to check that is that, are you using exactly as many integrators as the degree of the denominator polynomial, right. If it's an irreducible or a minimal transfer function with no pole and zero in common, and if you are using exactly as many integrators as there are as the degrees of the denominator polynomial, yeah, then you are sure that you are actually using a minimal realization of the system, right. So that's more or less like the story. But as of now we have seen, okay, that looks like some elegant new math, right, some elegant mathematical results, some beautiful results which you might appreciate, but functionally they don't have any use as such as of now, right. We've seen that, okay, we can realize a system using the minimal number of integrators, so probably that's economical. But what is its connection to some utility? In fact, so far in our studies of the state space system, we haven't even looked at how to design or synthesize controllers. Remember, when we talked about the classical control methods, we actually saw at least one method of designing compensators, such as lag lead, lead lag, yeah, and lag and lead compensators, and P, PI, PID, PD, those sort of controllers. We've seen how to design them. Although you might not be very happy with some of those design methods, as we've highlighted in the previous lecture. For instance, right at the end of the previous lecture we showed you that if you're given a transfer function like this, yeah, forget about performance, even stabilization is not possible using a proportional or a proportional plus derivative control action, right, because of this right half plane pole that's sitting over here. Now it turns out that this notion of minimality, that is synonymous with joint observability and controllability, yeah, will allow us to design controllers in the state space domain that are actually much more powerful. I mean, the method of designing this controller is much more powerful, yeah. So that is what we are going to study next, right. So for the time being, we will do well to remember that, well, minimality has this connection with fully controllable and observable systems, but let us get to the heart of the matter. So what sort of an action are we looking at? We have x dot is equal to ax plus bu, y is equal to cx plus du. Now remember that more often than not we will always assume that this du part, this is missing, so there is no feed forward, so we will assume that this is 0. You will see later on that even if it is not 0, it really does not make too much of a difference, yeah, but we will see shortly that yeah, it really does not matter if you consider this d or not, yeah. But so for ease of calculations or for ease of seeing things in a more transparent manner, we will for the time being assume that the transfer function is strictly proper rather than biproper. We will not consider the possibility that the transfer function is biproper, okay. So therefore this d term we can get rid of for now. So now consider what is the job of a control designer in this sort of a situation. The problem is as follows. The problem is that you have to design this u, remember, this u is basically the control action that is going into the system, alright. So our job is to, our task is to design this u, but how do we design this u, right? We want a sort of a closed loop action, we do not want some sort of a reference signal. So you might say, okay, apply a step, apply a ramp, apply a parabola, apply a sinusoid, yeah, these are the type of known signals. That is not the answer we are looking for. Remember what did we do when we designed controllers in the classical control domain using root locus, yeah? We fed back the output, right? So we had this plant, to that you had the input u, yeah, and then you had the output y, and then you fed back the output through a unity feedback channel, right, and took its difference. So it was a negative feedback, you took its difference from the reference or set point signal, and that was the error which was in turn fed to the controller. The controller spat out the actual output of the controller which goes to the plant, which is u, right. So the task is to design suitable u to meet performance metrics and also to stabilize if needed. So if needed means if the plant is not stable, then of course the first thing, for example, such a plant, for a plant such as this, of course you see that in the open loop there is a pole in the right half plane. So the first thing you need to do is to stabilize, then comes the question of performance. If it does not even stabilize, it does not make sense to talk about performance at all, it does not come into the picture. But now the restriction is that what sort of a u are we going to cook up? Earlier we saw that we were feeding back this output, but because the state space domain allows us this freedom of defining these states, which are of course non-unique from realization to realization, but we want to cook up. So the goal is cook up u using states, okay. So we want to cook up u as a function of x, so u as a function of the states, yeah. Not just that, so this is the first thing. The second observation is we do not want it to be a very complicated function of the states, right, because we have so far only studied linear systems. Now if you pass on something like minus x cubed or minus tan hyperbolic x, yeah, and things like that, and all such sorts of crazy functions that you can think of, yeah, then well it is not very helpful, is it, because we do not know how to analyze them. Of course if you study nonlinear control you will learn how to analyze some of these systems, yeah, at least qualitatively if not quantitatively in every case. Maybe you have to resort to numerical methods for that matter, but anyway that is a digression. So we do not want this, we want this to be a function of the states. Of course this state, remember, belongs to R to the n, but this u, because our case is just a single input single output system, so it is just a real number that it spits out at every instant of time. Yeah. Now the second restriction we see is that we want only linear functions of the states to be admissible as u. So what is a typical linear function of the states? A linear function of the states something like summation ki xi, I going from 1 through n, yeah, where of course x is given by x1 dot 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 till xn, right. So this is the type of control law we are looking at. Okay. Now you might at this point feel that this is very restrictive. Of course, when we are dealing with classical control methods such as root locus, even there our laws were all linear, right. After all, what did we do? We took the output, yeah, and then we sort of took its difference with the reference and then passed it through a controller. And what did the controller do? The controller either integrated, differentiated, or passed on a proportionally scaled value of that error, right. So it was eventually linear. So that same intuition tells us that maybe with this linear sort of a state feedback, yeah, so this is basically a linear state feedback, yeah. So with this sort of a linear state feedback, we want to test how far we can go or what its limits are. Limits as in not the mathematical limit, limit as in limitations, right, how far we can push the barrier, yeah, how far we can achieve our desired goals using just a control action of this sort. So you understand, first I want you to appreciate that this is a very restrictive class of state feedback we are allowing. It is just a linear state feedback, right, and you might feel a little let down. After all, what can this do? Is this worth much? Yeah, that is a question to ponder over, and it will turn out by the end of this lecture, hopefully you will see that it is worth quite a lot, because it does almost everything that we want it to do. Yeah. So let's take a closer look at this, shall we? So now, if we are saying that u is equal to summation ki xi, that can actually be written in this fashion, you see, till kn. So we can write this as an inner product or a dot product of this fashion, no, right. So then we call this matrix as K, okay, and of course this is x. So in general this u is then of the form u is equal to kx, where k of course belongs to 1 cross n, it is a row vector, yeah. So this is our control law. Now if we plug this back in, what do we get here? X dot is equal to ax plus bu, yeah. Now of course there is something else that is missing here. Well, strictly speaking, this is only the autonomous part of the response. Now of course you might have some, so for example you have this system here, yeah, and you are giving some reference input here, yeah. But now you are applying some sort of a feedback as well here, right, some sort of a state feedback that you are saying you are applying here. Then there is this k, so this double line is basically a vector of states, right, and then there is this C matrix which spits out this u. So this is this thing is my overall system, okay, yeah. So of course I have a B sitting here as well, yeah, but that is alright. So then we say that this is my overall system after the control action, right. So somehow it is as if I am saying, now we will come to this, we will revisit this point later. Remember that in the earlier case in classical control we were being able to tap out the sense signal from here, but now we are assuming that somehow we are allowed to get inside the system, because remember everything within this black dotted box is inside the system. So we are assuming that we are allowed access to these states at this level itself. So this is a double line, this is a state vector which upon passing through C turns out to be a scalar, so a single line here, right. So we are somehow assuming that someone is giving us access to these states. We will live with that assumption for the time being. Later on we will relax that subject to some other assumption and we will see it is still doable. So now the point is that then, well, you have this u one part of which is of course this kx that I have just said, and the other part is of course this this r of t, right. So this Laplace inverse of this big R is the small r, right. So this reference input has to be still there, no. So in the same, by the same token here, we will also add this term r of t here, yeah. So now if we plug this back in here, remember why this r of t is coming, because this part is just coming as the internal, something that is internal to the system, but this is the exogenous signal, the external signal, the excitation signal, right, that has to be always there, that is the externally applied reference signal. So therefore if we now take a look at this, this is going to be ax plus b, and if I substitute this I will get kx plus r, which then tells me that this becomes a plus bk times x plus br. So now you see that after this control action is applied, this becomes my closed loop system matrix, yeah, this was my open loop system matrix. Now this is my closed loop system matrix, and the A changes to A plus bk. You can check that the size of bk is n cross n, because b, remember, is n cross 1, k as I have said is r 1 cross n, so bk is of course n cross n. So of course this addition is valid, yeah, it is always a good practice to check this. So as you go from open loop to closed loop, yeah, with the state feedback, it turns out that this A changes to A plus bk. Not just that, there is this thing that about this k which is in my hands, so I can choose, yeah. So the A matrix of the system, yeah, that is a given, that is fixed, I cannot lay my hands on that, that is about the system's internal dynamics and its parameters and its system's ambient values and things like that, right. So that is intrinsic to the system, nothing I can do about it. So also is the B matrix, yeah, it is a function of all those systems parameters, but this k is something that I am choosing, that is of my choice, the designer gets to choose what this row vector k is going to be like. So it tells me that in doing this I may be able to shape, you remember when we were shaping the poles and zeros using root locus technique, or briefly when we delved into Bode plots we saw we were shaping the frequency response, yeah, by additional poles and zeros at suitable corner frequencies, right. So here also we are shaping the A matrix using this sort of a state feedback. So because I have the freedom to choose this k, I wonder if by choosing this k, that is these n parameters that I am free to choose, can I shape all the eigenvalues of A, yeah. So it will turn out that the equivalent condition for this is that the system's realization, state space realization, be fully controllable. So we will of course not go into a detailed proof, but because we have spent quite a bit of time on these Jordan forms and these minimal realizations and stuff, so we will give you some sort of a sketch or an idea of why it works. So it turns out that all the poles of A plus bk can be arbitrarily assigned or placed using k. This condition, yeah, is the same as AB pair is fully controllable. Now you might notice something here, I am using this term fully controllable, yeah, not just controllable. You might say okay, just my fancy, I am just using that term, just popped it in here, but there is an implication to that. Unfortunately again I will have to use that excuse that this is an undergraduate course, so we will not be able to delve into the details of that. What I mean by fully controllable is just what we have termed as controllable so far, which is to say that the controllability matrix is of full rank, full row rank, or in our case because it is CISO, it is going to be invertible, okay. So what if I am calling this fully controllable, does that mean that there is something called partially controllable? Well, if you cast your attention back to what we did, yeah, we took this T inverse AT, T inverse AT that would be, so this T inverse AT and we got to this Jordan form, yeah, and we took this T inverse B as well, and we got to this Jordan form of the B matrix as well, right. I do not know what I called it, did I call it J or AJ, whatever it is, but the point is that this J matrix, we had this sort of structures like, diagonal block, then lambda 1, this sort of real Jordan block, yeah, and then we had these A, B, minus B, A, yeah, all these possibilities. You just go back to the previous lecture and you will see that this sort of thing, and then we had this C matrix that looks something like this, and then we had the B matrix that looks something like this, of course, this is the Bj and this is the Cj, and this is of course the J. So then we inferred that either these blocks, these diagonal blocks in the Jordan form, yeah, they better not have repeated eigenvalues, yeah, because that will lead to that will lead to lack of both observability and controllability. And for controllability, we saw that, for the diagonal blocks, each entry of the B matrix corresponding to those states better be non-zero for controllability, right. Now what if some of them are 0? Then we will say that precisely those states are the ones that are uncontrollable, and you will see that those eigenvalues are the ones I can do nothing about, yeah. So that is precisely the point of this saying it's fully controllable. When we say it's fully controllable, it means every state can be independently maneuvered, and in other words, every one of these, remember these are the eigenvalues after all, right, and every eigenvalue can be given a nudge or pushed through the input, okay. So when we say fully controllable, it means every eigenvalue can be shifted, right. So therefore it makes sense when we say all the poles and this fully controllable, yeah. There are notions like stabilizable, yeah. What does stabilizable say? To put it very briefly, when we say a system is stabilizable, it means that there may be some modes of the system which are unstable, yeah, but at least those modes are controllable. So let me explain that slightly better in language. Suppose you have, again with an example maybe that will serve the purpose. So suppose you have lambda 1, lambda 2 and lambda 3 as the 3 eigenvalues, right, and let us say this lambda 1 is greater than 0, lambda 2 is less than 0 and lambda 3 is also less than 0, and you have the B matrix like 1 0 0, right. So this is suppose the B matrix. Then what can you say? You see this mode that is unstable, that is corresponding to this lambda 1, yeah, that has some control action acting on it. So the unstable mode can at least be controlled, yeah. So the next best thing to fully controllable realizations is a stabilizable realization, yeah. What is stabilizable? Stabilizable means, okay, I may not be able to control certain modes, but at least those modes are themselves stable. I may not be able to influence their performance, I may not be able to improve their performance, but at least they will not result in the system blowing up. So my inability to move certain states or maneuver or control certain states does not result in instability. Even though I do not have full controllability of the realization, at least the uncontrollable modes or the uncontrollable states are stable, yeah. So that even if performance metrics may not be met, at least stabilization may be met. So those systems are called stabilizable. If it is not fully controllable, then the next best thing we look for is stabilizability. Similarly for observability, there is this notion of detectability. So at least if those some of the modes are not observable, but at least those modes are stable, so that every unstable mode is reflected in the output, because hidden modes are something we are really scared of. If there are some hidden modes which are not reflected in the output, which cannot be influenced through the input, yeah, and if they are also unstable, then we are in real trouble, yeah, because then these modes will just blow up unbeknownst to us, because of some non-zero initial conditions. They will just blow up, nothing reflected at the output, nothing I could have done at the input to influence them, and yet the system blows up, right. So that is very dangerous, and that is precisely tantamount to having right half plane pole 0 cancellation, right. Think about it. I am not going to get into the proof of this or the details of this. Again, the details of these discussions will be within the scope of a multivariable controls course at the graduate level, but think about it. If you think about it a little and try to piece together the puzzle, the jigsaw puzzle pieces that I have left behind, you will be able to stitch together the story. The story is this: if it is fully controllable and observable, it is minimal, there is no pole 0 cancellation. If there is some mode which is not fully controllable, yeah, but at least that mode, I mean some modes that are not controllable, but at least those modes are stable, yeah, then I can deal with the remaining states which are controllable and they might afford to be unstable. I can still act on them and maybe place their poles. Of course, these all require proofs, we are not going to do those proofs, okay. So I am just trying to make you aware of the potential complexity of the problem, right, as you get into a more sophisticated and advanced course. For our purpose here, the CISO control systems, yeah, and for the undergraduate controls level, we will assume that it is fully controllable and we will push ahead and hopefully convince you by the end of this lecture that, well, this equivalence that you see before yourself on the screen here is indeed true, right. So enough discussion about this notion of stabilizability and detectability. If you are interested, you might read up on some standard textbooks at the graduate level, and I am sure you will find very nice descriptions of these properties. But let us move on ahead with this thing that we are discussing here, which is a pole placement, so called pole placement through this linear state feedback when the system is fully controllable, okay. So assume that it is fully controllable. So we start off with an assumption, assume that the realization ABC is fully controllable, yeah, which means that, of course, that the controllability matrix AB is, of course, in a multivariable controls course you would say it is full row rank. For our purpose, single variable, single input, single output, we will just say that the controllability matrix is invertible. Now observe, we have already laid the foundations for this. Note that we have already seen that if you take two realizations of the same transfer function and then you take this C1 A1 B1 times A, yeah, I think C1 inverse A1, yeah, times C1 A1 B1, yeah, this will be the same as if you take the second realization, yeah, in terms of A2 B2 and then A2 times, we have already proved this, so I am not going to go through the trouble of all this. Please revisit that lecture where we already discussed all of these in detail, right. So we have already seen this, and of course we know that if both A1 B1 C1 and A2 B2 C2 are controllable, then there exists a similarity transformation, because then both of these inverses exist. So for controllable realizations A1 B1 C1 and A2 B2 C2 of GS, we have this condition, right, we have seen this. So now the second observation we will make is that the phase variable canonical form is always controllable, yeah, this also we have seen. You see that the determinant, so this phase variable canonical form also has a name, it is also called the controller canonical form, as we have learnt in the maybe the last one or two lectures, yeah, and we will now see why that controller canonical form is so beautiful and why that lends itself easily to the design of a controller, which is why it gets its moniker, this controller canonical form. So we will see that we have also seen that this determinant in the phase variable canonical form or the controller canonical form, this determinant turns out to either +1 or -1 depending on the size of the A matrix, yeah. So it is independent of any other parameter, this is always going to be non-singular and invertible. So therefore this gives us the idea that given any realization, any fully controllable realization, let me add that, given any fully controllable realization, say A, B, C, we have the controllability matrix in terms of A and B, yeah, invertible, yeah. Corresponding to this same system, the phase variable canonical form or the controller canonical form if you like also exists and is fully controllable. Controller form realization, of course. So these are all about properties of the realization, not necessarily of the transfer function, okay. These are about the way you realize the state space system. So these are the two facts again, right. So given any fully controllable realization, we have this invertible, and corresponding to the same system we have the phase variable canonical form. So suppose the phase variable canonical form is AC, BC, CC, right. So now we know that in the controller canonical form we have this controllability matrix, yeah, CC of AC BC times AC, so of course this inverse, and CC of AC BC. This should always be equal to this original controllability matrix inverse times A times AB, right. So therefore it means that suppose my realization is x dot is equal to Ax plus Bu and y is equal to Cx, right. We've just chosen to ignore the D matrix for the time being, right. So suppose this is the situation, right. Then what can we say? Just now I want you to take a closer look at this. So can I not write this as, suppose x tilde is equal to, now observe very carefully what I am going to do here. So I am going to say that this CC CC of AC BC times C C of AB, I suppose that should be it, times x. Suppose this is true, suppose this is the way I am defining it. Oh, this is inverse, I am sorry, yeah. So you can be, for those of you who have paid attention and are very familiar with the idea of similarity transformation by now, you can immediately see what I am trying to do here, right. I am trying to basically get this AC to be written as some T inverse AT, yeah, where of course T inverse is equal to CC times C inverse, yeah. So that is my goal. So I already know my T inverse, so I am redefining my state variable like this. So look, this is nothing but the T inverse that I have just defined here, no. So that is what is going through my mind, I have now revealed to you, otherwise what I am doing here might at first glance appear to be like magic, but nothing like that, right. So again something we have done so often, then x tilde dot is equal to CC, I am going to drop this argument here, CC C inverse x dot is equal to CC C inverse Ax plus Bu, yeah. So that I can now write as CC C inverse A, and what do I substitute x as? I can just take the inverse of this T times, so what is T now? Look, the T is nothing but C times CC inverse, you can also see it from here, no, the inverse of this. So if this is going to be my T inverse, then T is going to be C and CC inverse, yeah. So I am going to just now write this as, if this is x tilde is equal to T inverse x, so x tilde is equal to T inverse x, therefore x is equal to T x tilde. I mean we have done this so many times, but it is always good to get some more practice out of this, right. So then this T is given by this, so I can just write this as C inverse times x tilde plus C inverse B u, right. So I can always go from this to this new description here, yeah. And now note that what is this? By my description here, yeah, this is nothing but AC. So now I have this sort of a transformation. So the idea is, whatever form you are given the realization in, once you have ascertained that it is fully controllable, you better find out, of course you have to find the controllability matrix in order to do that. So you have already found out this controllability matrix in your particular realization, and as far as the controllability matrix in the phase variable canonical form goes, it is very easy to evaluate and will be clear in a while. What is the phase variable realization typically? What does it look like? The AC will always look like this. I know exactly how it looks, yeah. Any other realization I may not be able to tell, but this one I know how it looks like, no, 0 0 1 like this, yeah. Then the last but one row tells me 0 0 0 0 like this till this one becomes 1, yeah. And then finally I have these coefficients all sitting here, minus A0 minus A1 dot 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 minus A n minus 1, yeah, and this is my BC matrix 0 0 0 0 1. So this is known to me, I know what phase variable canonical form or the controller canonical form looks like, yeah. That is the key observation, yeah. So I do not need to really evaluate, this is not just any arbitrary realization. Just like I knew how the observer canonical form looks like, that is the first realization we started with. That is why we also invested time on studying what the phase variable form looks like, the A and the B matrix structures, yeah. There is a certain structure to this, and that is precisely what we are going to exploit, yeah. So now that we have gotten here, we know that this is AC and this is my BC, that is it, yeah. So what are we now going to do? What is going to be our next key crucial step here? See let me summarize what we have done. Given any realization of the state space form in terms of ABC, you find out this controllability matrix C given by B, AB dot 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 till A to the n minus 1 B, yeah, and determine that its rank is full or that it is invertible, yeah. Once you have done that, then you just keep it aside for use later, and then with this form, you know what the denominator polynomial of your transfer function is, that is going to be the characteristic polynomial, isn't it, yeah. So I know that for this, the characteristic polynomial of AC, which is of course the same as the characteristic polynomial of A, yeah, because of course under similarity transformation the characteristic polynomial does not change, we proved that earlier. So many pieces coming together all at once, yeah. Here is the observation, the characteristic polynomial is very easy to evaluate in the phase variable canonical form. It is going to be nothing but A0 plus A1s plus dot 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 till A to the n minus 1 s to the n minus 1 plus s to the n, because it is going to be a monic polynomial, yeah. So based on my knowledge, what is this after all? In my GS transfer function, this is nothing but the pole polynomial, right. When there is no pole 0 cancellation, yeah, then the characteristic polynomial of the matrix A and the denominator polynomial in the transfer function, they are one and the same, yeah, there is no cancellation of any factors, right. So of course we have not yet talked about observability, so you might say hang on, there might be cancellation, maybe because you have realized it in the controllable form, it is not visible. Well, okay, we will revisit that, but for the time being at least you can see that even if you do not get this characteristic polynomial from G, at least for your particular realization you know what chi of A is, yeah, and once you know chi of A, you know precisely what AC and BC are going to look like. So here is the thing, given A, B, C, what do I know? I know controllability matrix in terms of AB. Second, I know the characteristic polynomial in terms of A, yeah. So these are these two I can independently evaluate, and from knowledge of this I know what AC looks like exactly, yeah, because I know this is a polynomial. Say I have evaluated this as a0 plus a1s plus dot 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 till an minus 1 s to the n minus 1 plus s to the n, and immediately after evaluating this I know what AC will look like, because I am going to just write AC as this whole 0 rows, this whole 0 column, then this identity matrix of size n minus 1 here, yeah, and this last row is going to be remaining here, and this last row is going to be filled up by minus a0, just the coefficients of the characteristic polynomial starting from the constant to the n minus 1th term, yeah. So this is going to be my AC, and once I know this, of course I know that I also know BC is equal to, this is irrespective of whatever the characteristic polynomial and everything is, this is just a property of the phase variable canonical form that the control action goes into the last term. So I know BC, so BC is going to look like this 0 0 0 0 1. So therefore based on this information now, so remember the first two I knew independently, given any realization I can evaluate the controllability matrix and find out if it is fully controllable. If it is fully controllable I proceed to the next step, yeah, if it is not fully controllable then I cannot do much about it with this method, okay. So for the time being we are assuming that it is fully controllable, okay. And then based on this what more do I know? Now that I know this AC and BC, I can also evaluate the controllability matrix in terms of this AC and BC, yeah, and then based on this I can of course now compute all of these, this T and T inverse, yeah. So then I can compute T, T inverse, etc. And once I have computed this T, T inverse, etc., I know exactly what transformation to take, yeah. So then I can go from x to x tilde clearly, yeah, because this transformation is what I need. So then I can use this red block here, right. Remember first I started off knowing this, yeah, then I know AC and BC how they look like, so I know this. Once I know this I know T, once I know T I know T inverse, once I know T inverse I know how to go from x to x tilde through this T inverse transformation, yeah, and that is it, that will be enough. So now you might say, okay, how does it help? Now notice the beautiful thing, once I am in this domain here, in the x tilde domain here, I have what? I have this AC x tilde plus BC U, yeah, but what is the structure of this AC? Now suppose U is equal to K tilde x tilde plus R, okay. Suppose this is my system's input, okay. Then what happens? Then I know that x tilde dot is equal to AC plus BC K tilde, or let me call this KC, yeah, to be consistent with the notation, yeah. This is in the, so once I have gone into the phase variable canonical form I am going to carry out my pole placement or my design of the gain K in this phase variable canonical form, and why? Because I am going to now see very shortly that this is very easy to do, okay, plus BC R, right. So this much at least I am assured of. Now look at the structure and why it is beautiful, 0 1 0 0 0 0 0 1 0, likewise you go to the last row here and then you have minus a0 minus a1 dot 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 till minus an minus 1, this is going to be this AC. What about this BC times K? This is going to be 0 0 0 0 1 times K1C K2C dot 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 till KNC, yeah, this is my KC matrix. So what does this lead to? This whole fellow looks something like this. Note that everything else is 0 in everywhere except the last row. In the last row what I have is just this K1C, K2C like this till KNC, yeah. So then what I have is this x tilde dot is going to be nothing but, if I am allowed to write this in a little more wider fashion, yeah, till the last row nothing changes because that addition of bk does not affect anything at all except in the last row, yeah. So this is what it is, and the last row, now notice this is minus a0 plus k1c, the second term is minus a1 plus k2c, similarly the last term is minus a n minus 1 plus k n c, yeah. This is going to be my a plus bk times x tilde plus bc times r. Now the question is, what is the characteristic polynomial of a plus bk, yeah. See, nothing has changed except for the fact that these coefficients have been changed by only these gains. So this I observed that in the same fashion as I knew that the, when you realize something in the phase variable canonical form, this is exactly what the characteristic polynomial looks like. You can take that as an exercise also, yeah, you just take si minus ac, the determinant of that, and you will find that in the last row you will find the characteristic polynomial's coefficients, okay. Take that as an exercise to convince yourself. Now this one I am going to say that it looks nothing but s to the n plus a n minus 1 minus k n times s to the n minus 1 plus dot 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 till a 1 minus k2c, so this knc, sorry, k2c times s plus a0 minus k1c. And now note, this is a polynomial of degree n, yeah, and n of whose coefficients I am allowed to tamper with. So if I am allowed to play around with all of these coefficients, I can reshape this into a new polynomial altogether. Whether it is a monic polynomial or not does not matter, no. So long as it is an nth degree polynomial, the coefficient of s to the power n is something non-zero. So therefore I can always divide the whole polynomial out throughout by this coefficient of s to the n and get a monic polynomial. So this, any nth degree polynomial's roots can be determined uniquely, not the polynomial itself, because obviously if you multiply the monic polynomial by any other factor, you will get a different polynomial with the same roots. So the roots of any polynomial of degree n can be uniquely determined, yeah, by n of these coefficients, yeah, particularly when they are coefficients of s to the power n minus 1, s to the power n minus 2, so on till the constant. So by my choice of these, I can arbitrarily reshape this polynomial. So I can reshape chi a plus bks solely using k, which is a row vector. There are only n terms and I need only n terms to perturb each of those coefficients and take them wherever I like. So for example, if I want a polynomial like, suppose my open loop polynomial is s cubed plus s squared plus s plus 1, yeah, and I want, so this is my open loop is equal to chi of a, yeah, and suppose my desired closed loop is I want s cubed plus 5s squared plus 7s plus 8, yeah. So then I better have chi of a plus bk equal this s cubed plus 5s squared plus 7s plus 8. Now what do I know? I know that this 1 minus k 3c is equal to 5, then this 1 minus, so this 1 is coming from here, this 1 is coming, so this 1 minus k 3c is equal to 5, so from 1 I need to go to 5, from this 1 I need to go to 7, from this 1 I need to go to 8. So 1 minus k 2c needs to be equal to 7 and 1 minus k 1c needs to be 8. So from each of these I can independently, this is not even a system of simultaneous equations, from each of these I can independently evaluate the k1, k2 and k3, and that way I have evaluated the gains, yeah, and I am done, right. So if you are already given a system in the phase variable canonical form, then note that this first few steps you do not have to do, this going from this one to the other, But once you are in the phase variable canonical form or the controller canonical form, it is very easy. That is why it is called a controller canonical form, you see, because it is very easy to read off independently what those individual gains are. Just look at the open loop polynomial, open loop characteristic polynomial, the desired closed loop characteristic polynomial, and take the difference between those coefficients, and those differences are exactly those gains. Yeah, so it is a fact that these gains are uniquely determined. This is a fact that is only true for the CISO case, by the way. In the multivariable controls case, you will see that because you will have multiple channels of applying the inputs, the choice of these gains k are not unique. So that is one of the points where the results deviate between the CISO and the MIMO case, right. When you study multivariable controls, you will see that you can still place the poles if the system is controllable, but the choice of the gains is not unique, not necessarily unique, okay. So here it is unique, but we are not done yet. What is still remaining? What is still remaining is, note that we started from a realization in terms of ABC, then we took the similarity transformation, went from x to x tilde, yeah, and now in this x tilde domain, in this controller canonical form or this phase variable canonical form, we have evaluated this kc. So now we know kc, but the question remains, what about k? What is k? Remember, eventually my realization is not in the controller canonical form, the realization is in form of ABC. So I need to find out that in my original realization, excuse me, what should be my k matrix, the gain matrix, such that, so that A plus BK has the same desired characteristic polynomial, yeah. So I know that if I apply kc, k1c, so if these are my values, right. So if I apply, say, minus 7, sorry, not comma, so if I apply in this case, for example, if I apply kc is equal to minus 7, minus 6, minus 4, yeah, I know what is kc. So this kc can be applied in the controller canonical form or in the phase variable canonical form in this form. But that is not good to me, right, because my form, this is just an artifice that I have created. I started with an actual realization which is in terms of ABC. I saw that mathematically I can cook up this, because we have seen earlier that we can go from any controllable realization to any other through a similarity transformation. So that is why I cooked up that similarity transformation and went from my realization to the controller canonical form or phase variable canonical form realization. And then I have found out that it is very easy to design what the gains are in the phase variable canonical form. But that is not the complete picture, no, that does not end the story. Now I need to be able to go back to this system that is actually existing, that has actually been realized before me, right, and I need to be able to say what the k is. This kc that I am applied here in the controller canonical form will not work here, yeah. So what is it that should work here? Well, the answer is again in the similarity transformation. You see, I have x dot is equal to ax plus bu. Now note that the u is still the same, u is still the same whether I apply it to ABC, my actual realization, or to AC, BC, CC, which is the phase variable canonical form or the controller canonical form, yeah. Now what then should this be? This is, I know what this is Ax plus B, and what is this u? This was nothing but Kc x tilde plus R, yeah, and now I have already got my recipe. What is it going to be? So this is the crucial observation, key observation. Why should this be true? Why is this key observation true? Remember that after all, what is this? This is some system. You are applying some u here through some control action, and this is that same system after all, which is leading to the same transfer function, and you are applying the same u here, no. So whether you apply the u in terms of x tilde or in terms of x, they had better be equal, otherwise the control action will be applied differently to the same system, no, yeah. So therefore what this tells me is that this is Ax plus B, and now I have to go from this x tilde to x, and that is simple. I know how to go from this x tilde to x, right, yeah. So I know that x tilde is equal to T inverse x. What is T inverse? This is C inverse, sorry, so this is C inverse, yeah. So then I know that this is going to be nothing but Kc and C inverse x plus R. So that means my system turns out to be A plus B Kc Cc C inverse times x plus Br. So effectively that means it turns out that this is my K. So my K in this domain is going to be nothing but Kc times Cc times C inverse. Remember, I know each and every one of them now. Why do I know each and every one of them? I know Cc because I know what AC and BC look like, and therefore I know that what Cc looks like. I know C because obviously I know A and B, which is my realization here, so I know this, and I know Kc because that Kc was very easily evaluated in the last step where I showed you how in the phase variable canonical form it is very easy to evaluate the Kc, yeah. Each term independently ascertains one coefficient of the characteristic polynomial, yeah. So from going from the open loop to the closed loop, what is the difference in each coefficient? That difference is catered for by the gain in the controller or phase variable canonical form, right. So therefore I know Kc. So now once I know every one of them, I know what K I must apply. But what is this C inverse? If you go back a few slides when we wrote this, what is the C inverse? It is nothing but yeah, this is nothing but T inverse. So essentially what we have derived here is that this is going to be, this K is going to be nothing but T inverse, sorry, Kc T inverse, it's going to be Kc times T inverse. So this sort of simplifies the calculation. Now of course you might argue that wait, you have said that you have to evaluate the controllability matrix and take its inverse and do all these sort of things, right. So that does not sound very appetizing to me, right. I mean I have to still evaluate this controllability matrix, take its inverse, and if it is beyond size 3 by 3 then well I am in a soup, right. So I do not want to have to evaluate all these inversions and all unless I am forced to. So well, this only serves to show or prove that if you have the controllability assumption going, then this method will always work. But it is not necessary that you have to always, given any realization, go to the phase variable canonical form, design the gains in that domain, and then go back to the original domain through this transformation again, Kc times T inverse, and design and then say that this is my gain. This is only to show you that provided your realization is controllable, there exists a unique gain that will take you from your open loop characteristic polynomial to whatever your desired closed loop characteristic polynomial is, which defines your closed loop poles, right. But in general what I am saying is you do not necessarily have to follow this step. What you have to do is, what you can do is this. So suppose I have this x dot is equal to Ax plus Bu, y is equal to Cx, right. So what I say to myself is, well hang on, this is x dot is equal to Ax plus Bu. Suppose I have ascertained that, so suppose this CAB is invertible. So suppose I have ascertained that this realization that is given to me, not necessarily in the phase variable canonical form, in any form, this is invertible. Then what I do is I can avoid going through that, to transforming it into the phase variable canonical form and then again retransforming the gain matrix that way. So because I now know based on this discussion that provided there is this controllability condition that holds true, I can always find a unique gain K. Let me just directly go ahead and find that gain K instead of going through all this roundabout fashion. So let me just directly say, let K is equal to K1 dot 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 till Kn, whatever the structure of this is, and then I need determinant of Si minus A minus Bk is equal to the desired closed loop characteristic polynomial, yeah. So this is given to me, note that this is given to me, yeah, I have been already told either directly or indirectly by some performance metrics that I need this much damping, I need this much percentage overshoot, I need this much settling time and all. and that way you can determine where your poles ought to be, right. Either directly they will tell you place your poles at -10, -50, -500, or I can tell you that this is how your poles should be placed by performance metrics. Either way, I know this polynomial has to be already given to me. Of course, if you want to not go directly there and you want to do this in an optimal fashion, then you have to go for optimal control methods, which is again basically linear quadratic regulator, another pole placement method, but in an optimal fashion it places poles. We will not get into that. The point is that this is always going to be known to you, this closed loop poles where they ought to be. So then the only unknown here is this, and there are n unknowns. So what you might wonder that if this is so simple, then why did we bother to go through that trouble of this phase variable canonical form? Well, one, we wanted to show you that it exists and is unique. So that proof is only a possible, or rather one of the easy ways to see that proof is to go through this route of phase variable canonical form. The second is that in the phase variable canonical form we saw that each of those coefficients are decoupled, each gain is entering exactly one coefficient. Yeah. So although this is a equation in n variables, n equations in n variables, but each of those equations contain only one variable and the other variables coefficients are 0. It is a decoupled system of equations. Here the price you will be then paying is that whatever computation you want to save in terms of computing this controllability in the phase variable canonical form, taking its inverse and all that, which might appear pretty cumbersome, yeah, but at the end of the day what you will have to do is you have to solve for n equations in n variables, and you will see that those are not necessarily decoupled. So you will see that in some of the coefficients of this closed loop characteristic polynomial, multiple of those gains are entering, yeah. So it will be like a coupled system of simultaneous equations, yeah, n equations in n variables. So these are linear simultaneous equations, yeah. So that is the price. So this is the second method which many people actually prefer, yeah, although it is not a system of decoupled linear equations and it is not very transparent to see what the gain k will be directly from the coefficients, unlike in the previous case, but yet this method avoids all the pitfall of computing this controllability, although eventually you will see that you will be inverting a matrix at the end of the day. If you want to solve for n equations in n variables, you have to invert some matrix or the other, but the good thing is that it does not make you go about in this apparent roundabout fashion. So if you are given a system already in the controller canonical form, it is the easiest thing, yeah, just find out what your desired closed loop polynomial is, take the difference between the coefficients, those will be your gains. If you are given in any other form, one option before you is convert it to the phase variable canonical form, determine the gain coefficients in the phase variable canonical form, and then operate it with this T inverse post multiplication and get the original gain that you need. Or you might bypass all of that because you know that your realization is controllable, start with your original realization, let those gains be some unknowns k1 through kn, yeah, then evaluate this determinant with the k's being unknown, and then look at the coefficients of s in this polynomial and in this polynomial which will be given to you, and by comparing those you generate n equations, n variables, solve them. And the reason why this will always be solvable is again because I have already shown you that this solution will exist provided it is controllable. So with that we will at least have established before you that if your realization is controllable, you can always place the poles arbitrarily anywhere you like through state feedback. So in the next class when we come back, we will see that this is not just a sufficient condition, that is, this controllability is not just a sufficient condition for the ability to place your poles anywhere, but it is also a necessary condition. So we will just quickly see in the next lecture at the beginning that if your system fails to be fully controllable, if some of your modes are not controllable, then aided by the Jordan form we have seen earlier, we will be able to establish that well you will not be able to place those particular poles, yeah. So not all of your poles will be placeable arbitrarily, yeah. So that is why we will then establish that controllability is not just a sufficient condition as might be apparent from this lecture, but it is also a necessary condition for your ability to place your eigenvalues of the closed loop system or the poles anywhere in the complex plane.